Let's start with a couple of practice problems. So go ahead and hit pause on this one, and I will be right back with the solution. So this problem is pretty straightforward. We're asked to solve for the pH of a 0.01 molar perchloric acid solution. And we should recall that perchloric acid falls into one of our 7 strong acids. Strong acids, again, they completely dissociate. So if we know the concentration of strong acid, then we know the concentration of hydronium in solution. Plug that into your calculation for pH, and you will get a pH of 2. This next problem is a bit more challenging. Go ahead and see if you can figure it out without doing any actual calculations, and I'll be right back to discuss it. Understanding that strong acids completely dissociate and weak acids are in equilibrium is vital to solving this problem. So we know that the concentration of a strong acid is equal to the concentration of hydronium in solution. But what about a weak acid? Does the concentration of a weak acid equal the concentration of hydronium in solution? The answer is no, because it doesn't fully dissociate. So the concentration of hydronium in solution is going to be less than the concentration of your original weak acid. So we know from the previous problem that the concentration of this strong acid would give a pH of 2. Because hydrofluoric acid is a weak acid, it is not going to have the same concentration of hydronium as a strong acid would, but it also will have a greater concentration of hydronium than pure water would have. So that puts our concentration of hydronium for this hydrofluoric acid solution somewhere in between. So when we evaluate our viable answers, we know that we don't have a pH of 2 like the strong acid, and we know we don't have a pH of 7 like pure water. And being a weak acid, we know that our pH wouldn't be below the pH of 2 of the strong acid. That leaves us with the answer of the pH being greater than 2. By how much, we don't really know, but we're about to get into that next. So just how do we measure the pH of solution? Well, there are a few ways we can do that. One is by using litmus paper. Red litmus paper will turn blue above pHs of about 8, and blue litmus paper will turn red below pHs of about 5. But you'll see that this leaves sort of a big range and not a really accurate indication of what pH our solution is. The other way is to use an indicator. These are a variety of molecules that we add in a very small amount to a solution. And based on their molecular structure, they can change color with respect to the pH or the hydronium in solution. You've probably used phenolphthalein in the lab when performing an acid-base titration. A more accurate way of measuring pH of solution is by using a pH meter. It acts as a voltmeter that measures the concentration of hydronium ion in solution. So we can calculate the weak acid dissociation constant from the pH of a solution. So let's take this problem. The pH of a 0.1 molar solution of formic acid at 25 degrees Celsius is 2.38. Calculate the Ka for the formic acid at this temperature. Let's start by writing the balanced weak acid equilibrium process. And from that, you can write your weak acid dissociation constant expression. Now, the other piece of information we were given was the pH of this solution. From the pH, we can calculate the hydronium concentration. This hydronium concentration is the concentration at equilibrium. So now we can use this value to solve for the acid dissociation constant, the Ka of formic acid. Now we can set up our RICE table. RICE stands for reaction equation, initial concentration, change in concentration, and equilibrium concentration. Initially, we have zero point 0.1 molar formic acid, but we haven't proceeded to form any hydronium or formate yet. As the reaction pushes to the right, we can evaluate the changes in concentration of each species with respect to some concentration x. And the magnitude of x depends on the coefficient in front of each species in the balanced reaction equation. In this case, all of our coefficients are 1. So formic acid will go down by 1x, and hydronium in formate will go up by plus x. Now, do you know the value of x? It was the concentration of hydronium we found using the pH value. X is equal to 4.2 times 10 to the minus third molar. So let's plug that into our Rice table and calculate for our equilibrium concentrations. Now we can go back to our weak acid dissociation constant expression, plug in for our equilibrium concentrations, and solve for the Ka. We can also calculate for the percentage of our original weak acid molecules that ionized or that went through dissociation to form hydronium. This is called percent ionization, and this calculation is going to come in handy when we get to more complex problems and want to determine if we can avoid using the quadratic equation. Calculating the percent ionization of a weak acid or a weak base takes that equilibrium concentration of hydronium for the weak acid or hydroxide for the weak base over the initial concentration of that weak acid or weak base times 100 and gives us the percent ionization of that species. So for the formic acid problem that we just did, take your equilibrium concentration of hydronium, your initial concentration of formic acid, and plug it into the percent ionization equation. And calculate the percent ionization of this formic acid solution. Now, I mentioned that this equation can be used down the road when we do more challenging problems. Percent ionization of 5% or less indicates that we can make some assumptions when we're solving our Rice tables with respect to x that might help us avoid solving for the quadratic equation. So make a little mental note of this, and we'll show that in the next problem. So let's get to it and calculate the pH of a solution of a weak acid solution from its weak acid dissociation constant. Calculate the pH of a 0.3 molar solution of acetic acid at 25 degrees Celsius. So we've got our balanced equation for the weak acid dissociation. We've been given the weak acid dissociation constant for acetic acid of 1.8 times 10 to the minus 5. Go ahead and write your weak acid dissociation expression for this reaction. And here's what you should come up with. The weak acid dissociation constant, Ka, is equal to the equilibrium concentration of hydronium times the equilibrium concentration of acetate over the equilibrium concentration of acetic acid. Now we can go ahead and fill out our Rice table as we did before, what we would do with any equilibrium problem, where we have our reaction species, our initial concentrations, our change in concentrations, and our equilibrium concentrations. Unlike the previous problem we did, we don't have any values for our changes in concentration of any of our species or equilibrium concentrations of any of our species. So we're going to have to stick with x and plug it back into our equilibrium constant expression. And we can see as we follow the math through to solve for x, we're going to be left with having to solve for a quadratic equation. Ew. Now, despite the way we all feel about solving a quadratic equation by hand, it will always give you the correct value for x, assuming you get through all the steps without making any mistakes. What we want to do is take advantage of situations where we can avoid having to solve for the quadratic equation. And this is where the 5% rule of percent ionization comes in handy. So let's get rid of all this quadratic equation mumbo jumbo and take a look at what I'm talking about. Do you see how this dissociation constant 1.8 times 10 to the minus 5 is pretty small compared to the initial concentration of zero point 0.3 molar acetic acid. The general rule is that when they're about 3 to 4 orders of magnitude apart, the value of X is going to be insignificant compared to your starting concentration. So let's do this. Let's assume this X is small and let's get rid of it. And look at how we can solve for X without having to go through a quadratic equation. Now we solve for X, which would be the equilibrium concentration of hydronium, which is what we're concerned with trying to solve for pH. But before we do that, we want to double check our assumption. Let's make sure that by ignoring the X here in the initial concentration of acetic acid, which helped us avoid doing a quadratic, let's check that percent ionization and make sure that we obey the 5% rule. And look at that, our percent ionization is less than 5%, which validates our assumption to get rid of that X, and we're good to calculate pH. So let's take this and let's do a couple of more problems. Calculate the percent of niacin molecules, here's the acidic proton right there, ionized in a solution that is A, 0.01 molar, and B, 0.001 molar. 1 times 10 to the minus 2 versus 1 times 10 to the minus 3. I'll also have you calculate the pH of these solutions. Go ahead and get started on A, and I'll be right back with the solution. Did you hit pause? Did you try it? Hit pause. All right, we're back. We're going to start with a generic balanced reaction equation for the dissociation of a weak acid and the weak acid dissociation constant expression. From here, go ahead and create your Rice table, fill in your initial concentrations, your change with respect to X, and your equilibrium concentrations with respect to the change in X. And then you can go ahead and fill those equilibrium concentration values into your equilibrium constant expression. At this point, you can either solve for X using the quadratic equation, or we can make the assumption based on our starting concentration of niacin and the equilibrium constant or the acid dissociation constant for niacin being far enough apart that we can assume that this X is negligible. So we're going to go ahead and do that. And before we can proceed to solve for the pH of this solution, we need to double check our assumption by solving for the percent ionization equation. And with a percent ionization of 3.9%, which is less than 5%, our assumption to get rid of the X is valid. So now we can go ahead and solve for the pH of this solution. Let's try that exact problem, only let's change the starting concentration to 1 times 10 to the minus 3 molar and see where that takes us. I'll give you a hint. Get your quadratic equation ready. Now hit pause and do it. Go ahead. All right, we start out the same way with our Rice table and our equilibrium constant expression. From here, you can fill in your initial concentrations, change in concentration with respect to X, and equilibrium concentration with respect to that change. And then we plug those equilibrium values into our equilibrium constant expression. Now let's take a look at getting rid of this X again, comparing the concentration this time, 1 times 10 to the minus 3, with our equilibrium constant 1.5 times 10 to the minus 5, it's only about 2 orders of magnitude difference. So let me show you what happens when those values get closer and how we cannot make that assumption. So we've gotten rid of the X here and here. So now we can solve for X in just the way we did on the previous problem. But you'll notice that this value for X, which would be hydronium concentration, isn't so insignificant compared to that starting concentration of our acid. So let's go ahead and do percent ionization calculation and see what we come up with. And we see that it's greater than 5%, which means that our assumption was not valid. We need to go back and solve for the quadratic. So having replaced our x's, we can now go in and set up for our quadratic formula. Now we can very carefully solve for the quadratic equation, solve for x, and determine which x makes sense. Remember, one of them won't be valid. Now we can solve for the percent ionization and pH of this solution. So there you have it. I would recommend getting some practice on these types of problems before moving on to the next section. We'll see you.